How do you convert between a Fischer and a haworth projection? The first thing you're going to do is count your carbons. You're going to go all the way from carbon 1 down to carbon 6 so that when we convert to our haworth projection, we can make sure we're working on the right carbon and that when we look at the substituents and the directions, you're going to see exactly which carbon you need to be working on. You're then going to determine if it's the L or the D isomer. You can do this by looking at the penultimate carbon, the second to last one, and look at the direction of that OH group. If it's on the right-hand side, it's going to be the D isomer. If you speak Spanish, this is derecha, D. And if it's on the left-hand side, it's the L isomer. You're then going to turn the whole molecule 90 degrees clockwise. A way you can do this is by grabbing the top with your right hand, grabbing the bottom with your left, and rotating it to be flat. Once you do this, you'll notice that all the OHs that were on the right-hand side are going to be at the bottom. Look at carbon 2 on the Fischer and look at carbon 2 here on the haworth. If you notice, all the ones that are on the left-hand side of the Fischer projection are going to be on the top. Look at carbon 4 on the Fischer and look at carbon 4 here on the haworth. The last thing that you're going to notice is that when we look at carbon 5, we see that there's some interesting information. This OH on carbon 5 actually carries out the nucleophilic attack. This is the one that attacks that carbonyl carbon in the aldehyde group of this particular Fischer projection. Now, once that happens, we see that this oxygen on carbon 5 in the OH, that oxygen is going to end up becoming the oxygen inside the ring. This is actually going to be pretty much that one right over there. Once that forms, we'll notice that this OH, actually, it can't be on the top or the bottom of this particular ring. It's in the ring itself. So what do we have to look for? The CH2OH. The CH2OH, think of it as being on the opposite side of the OH. If this was the D isomer, our CH2OH should be on the top. If this is the L isomer, the CH2OH should be on the bottom. Once you have that information, the last thing to determine is if we're working with an alpha or beta molecule. So how can we determine if we're working with the alpha or beta anomer? Technically, we can't. This hydroxide group, which is carrying out the nucleophilic attack, can either attack in front or behind of the carbonyl group. That's going to be that aldehyde or ketone group that we're working with. Now, upon this ring closure, the oxygen that was on that carbonyl group is going to be forming this new hydroxide here on carbon 1. Now, it can be a different carbon, but in our particular example, this is carbon 1. It can be on either the top or the bottom of that particular molecule, depending on the direction that this OH attacks it from, but it's random chance. So unless the question tells you provide the alpha or the beta anomer, both are likely. Now, with this in mind, how can we look for the alpha or beta anomers of this particular projection? Well, alpha, think alpha antagonist. They're on opposite sides. So CH2OH, this CH2OH right here, this is on the top of the plane, so we should expect that our OH should be at the bottom of the plane, the OH on the anomeric carbon. If we're working with a beta projection, then we should expect this CH2OH over here to actually end up being on the same end of the plane, meaning our OH on the anomeric carbon should be right here. So you can think beta, bullhorns, they're on the same end, they kind of look like bullhorns. Alpha, antagonists, they're on opposite ends. I hope this helps.